After studying this module, you shall be able to learn about primary salt effect and secondary salt effect. Let us begin with introduction. In our last two modules, we took up solution kinetics in detail. You now know that solution kinetics is the kinetic study of chemical reactions taking place in solution phase, and the nature of solvent has a predominant influence on the kinetics of such reactions. In general, the solution phase reactions can be classified as ionic reactions and non-ionic reactions, and here we are concerned with the kinetic study of ionic reactions. We found that only classical thermodynamic approach of transition state theory can be utilized to determine the rate constant of ionic reactions or solution phase reactions, and even studied the effect of solvent on rate constant in our last two modules. In this module, we will focus on primary salt effect and secondary salt effect. Before trying to understand what is primary salt effect and secondary salt effect, let us understand what is salt effect. It has been observed that rate of a reaction can be altered by the presence of non-reacting or inert ionic species in solution phase. This effect is profound when the reactions take place between ions even at low concentrations. Now, this influence of charged species on the rate of reaction is referred to as salt effect, and this salt effect is classified as primary salt effect and secondary salt effect. Both these effects are important in the study of ionic reactions in solution phase. Over here, we will first take up primary salt effect. The primary salt effect takes into account the influence of electrolyte concentration on the activity coefficient and hence rate of the reaction. Let us consider a simple transition state complex, or rather we shall consider a simple reaction A plus B giving AB star giving products, where AB star refers to as transition state complex and K star is the equilibrium rate constant for this reaction A plus B giving transition state complex. So, this K star can then be written as, in numerator, activity of transition state complex upon, in denominator, activity of reactant A into activity of reactant B, which further becomes equal to concentration of AB, that is the transition state complex, in numerator, divided by concentration of A into concentration of B whole into, in numerator we have gamma star, which is the activity coefficient for the complex, upon, in denominator, gamma A into gamma B, which are the respective activity coefficients of reactant A and B. On rearranging this equation, we obtain the equation in terms of concentration of transition state complex AB. So, AB star concentration becomes equal to K star into concentration A into concentration B into gamma A into gamma B upon gamma star. Now, the rate of such a reaction is given by the expression R is equals to KBT upon H into concentration of the transition state complex. On substituting the value that we have obtained for the concentration of transition state complex here, the rate equation becomes equal to KBT upon H into K star into concentration A into concentration B into gamma A into gamma B upon gamma star. Experimentally, the rate of such a equation A plus B giving products is given by the expression rate is equals to K into concentration A into concentration B. Now, if we compare this equation, that is rate is equals to K into A concentration into B concentration with the rate equation that we have obtained from transition state theory, that is KBT upon H into K star into concentration A into concentration B into gamma A into gamma B upon gamma star. We obtain the expression for K as KBT upon H into K star into gamma A into gamma B upon gamma star. This further reduces to K is equals to K naught gamma A into gamma B upon gamma star. Now, we did derive the same expression in our earlier module while discussing transition state theory, where we considered the concentration terms in place of activity for the sake of simplicity. Over here, we have considered the same derivation more explicitly in terms of activity, which is expressed as product of activity coefficient into concentration. So, K naught becomes the rate constant when all the activity coefficients approach. So, K naught becomes equal to the rate constant when all the activity coefficients approach unity. Now, if we use the expression K is equals to K naught gamma A into gamma B upon gamma star and we take logarithm on both the sides, we obtain the expression log K is equals to log K naught plus log gamma A plus log gamma B minus log gamma star. Now, activity coefficient varies with the concentration, especially in the presence of an added electrolyte. We studied a term called ionic strength in our earlier module. This term was introduced by Lewis and Randall and is a measure of intensity of electric field due to the ions present in the solution. Now, ionic strength is expressed as a cumulative measure of both charge on the ion as well as its concentration in the solution. It is mathematically expressed as 1 upon 2 summation Ci into Zi square. According to Debye-Huckel limiting law, this activity coefficient is related to ionic strength as log gamma is equals to minus q z square under root ionic strength, where q is a constant which has an approximate value of 0.51 for aqueous solutions at 25 degrees Celsius. Now, since the charge on an activated complex or a transition state complex is Z, which is Za plus Zb, this equation can be rewritten as log K is equals to log K naught minus Q, within brackets we have Za square plus Zb square minus Za square minus Zb square minus 2 Za Zb into under root ionic strength. This simplifies to the form log K is equals to log K naught plus Q into 2 into Za into Zb into under root ionic strength. Substituting the value of Q as 0.51 for an aqueous solution at 25 degrees Celsius gives the expression as log K is equals to log K naught plus 1.02 into Za into Zb into under root ionic strength. Now, this equation has been used a number of times and a plot of log K versus under root ionic strength gives a straight line with slope which is equal to 1.02 into Za into Zb and intercept as log K naught. The graph is there on your screen and as you can see, sign of Za Zb determines the direction of slope. If one of the reactants is a neutral molecule, Za into Zb is 0 and rate constant is expected to be independent of ionic strength. So, we obtain a straight line as shown in the graph. However, if the reactions involve similarly charged ions, Za Zb will be positive and slope of straight line will be positive. That is, the rate of reaction will increase on addition of an electrolyte. On the other hand, if the reaction involves oppositely charged species in rate determining step, then Za Zb will be negative or product of Za Zb will be negative and rate of reaction will decrease on decreasing ionic strength, that is on adding salt in reaction mixture. Some examples with different combinations of Za and Zb are there on your screen. For the first reaction, the product ZA into ZB is 2, which means a positive slope. For the second reaction, ZA into ZB is 0. That means log K versus under root ionic strength is a straight line. And in the third case, ZA into ZB, that is the product, is equal to minus 2, which means a negative slope. So, in primary salt effect, addition of an electrolyte or variation of ionic strength affects the activity coefficients and hence rate of the reaction. Now, moving on to secondary salt effect. The secondary salt effect is the actual change in the concentration of the reacting ions resulting from the addition of electrolytes. In a reaction where H plus or OH minus ions produced from a weak acid or a weak base act as a catalyzing agent or a catalytic agent, the addition of salt influences the concentration of H plus and OH minus ions. Since the rate of reaction depends upon the concentration of H plus ions or OH minus ions, it is well affected by salt concentration. Now, this phenomenon is referred to as secondary salt effect. Let us try and understand this in more detail. Let us consider a reaction which is catalyzed by H plus ions produced by a weak acid, that is acid catalyzed. The dissociation of this acid is given by the equation HA giving H plus plus A minus ions, and the dissociation constant Ka for this reaction in terms of activity coefficients and concentration is given as concentration of H plus into concentration of A minus upon in denominator concentration of the weak acid HA into gamma H plus into gamma A minus in numerator divided by gamma HA. On rearranging this equation to obtain the expression for H plus ion concentration, we obtain H plus ion concentration as K into gamma HA upon gamma H plus into gamma A minus, where K is equals to Ka into concentration of HA upon concentration of A minus. Now, if we compare this equation with that obtained experimentally, where rate is equals to K into concentration A into concentration B, and this equation, we obtain K as K naught into gamma HA upon gamma H plus into gamma A minus, where K naught again is the rate constant in absence of secondary salt effect, but it includes the primary salt effect. Now, this equation at 25 degrees Celsius takes up the form log K is equals to log K naught plus 1.018 into under root of ionic strength. This equation is very much similar to the one that we derived for primary salt effect. So, when ionic strength increases, the concentration of H plus ion increases and therefore, rate of acid catalyzed reaction also increases. Similar results are obtained for reactions catalyzed by hydroxyl ions. So, the ionic strength must be kept constant while examination of general acid base catalyzed reactions, because if ionic strength is not constant, the rate constant will change. Let us summarize what all we have learned in this module. Solution kinetics is the kinetic study of chemical reactions taking place in solution phase, and nature of solvent has a predominant influence on kinetics of such reactions, as we have seen. In this module, focus was laid on primary salt effect and secondary salt effect. It has been observed that rate of a reaction can be altered by the presence of non-reacting or inert ionic species in the solution. This effect is profound when the reaction takes place between ions, and this influence of charged species on the rate of the reaction is referred to as salt effect. The primary salt effect takes into account the influence of electrolyte concentration on the activity coefficients and hence rate of the reaction. Whereas, the secondary salt effect is the actual change in concentration of the reacting ions resulting from addition of electrolytes.